Hey, good afternoon. I'm Stefan Brudzinski, the EUMETSAT third generation user preparation project manager at EUMETSAT. I'd like to welcome you to this second day of this webinar on the next generation MTG Lightning Imaging mission. We have had an exciting day yesterday with an overview of the Lightning Imager, consideration on processing performance. We had next to 200 participants yesterday and a very lively Q&A session. So it was a great day yesterday, and I welcome you to this session today, which is focusing on the actual testing of the system once it's in space, so the commissioning phase, on the measures that EUMETSAT is taking to validate and monitor the performance of the Lightning Imager. And I'm very pleased to have also representatives from two European meteorological services, from Meteo France and KNMI the Netherlands, with us, who will speak about their first experiences in using space-based lightning mapping data and their plans to use LI. To put the mission in context, I'm showing just 3 slides on MTG as a whole. So the MTG consists, when it's in full operational configuration in 2025, consists of 2 imaging satellites, both of which will have the Lightning Imager on board, and both of them will also have a spectral imager, the flexible combined imager, one providing the full scan service and one the rapid scan service. In addition, we'll have the sounding service in the center. The start of operations of the first imaging satellite is planned for 2023, with an operational exploitation planned for about 20 years. And I have a nice animation to show to you, which just shows the functioning of this. This is the full operational constellation. This is the first imaging satellite. We have the Lightning Imager with its 4 cameras, the flexible combined imager. Because they are co-located on the same platform, I'm showing here also an illustration of the scanning principle for the full disk scanning service provided by FCI, and the Lightning Imager, which continuously detects lightning here, as you can see, over Central and West Africa and Western Europe. And they provide also geophysical products, which are illustrated here by these icons. And just to be complete, I also show you the rapid scanning service, which is complementing this. Okay. So with that introduction, I'd like to hand over to my first speaker, is Bartolomeo Vitichier from EUMETSAT, the LI team leader, will speak about the commissioning plans. Bart, the floor is yours.
Can you see the slides?
Not yet in presentation mode.
No?
Yes, now it's good. And
Good.
if you could switch on your camera, at least briefly, if you may.
I've tried earlier, but apparently I'm not allowed.
Okay, keep going.
So good afternoon, everybody, again. Thank you all for joining. So yes, today I'm gonna give a short overview about the system commissioning and the system commissioning plan. And together with these, we will also show on which aspects we are already preparing, getting ready with quite some work on the implementation of the DLI Star offline tool that then will be presented by Sven-Erik. So the outline is a very simple talk, introduction. We will talk about the EUMETSAT plan and then discussion, of course. So the objective of the commissioning of any system, but today we will talk about LI, of course, is to demonstrate the, to ensure that the capabilities of the system are demonstrated in operational configuration under operating conditions. The main goal of the commissioning is to establish sufficient and objective confidence about the readiness of the system, allowing the handover of the MTG spacecraft operational responsibility, corresponding ground segment and services to the operations department in EUMETSAT named Ops. Nominally, the duration of the commissioning for LI is planned to be 1 year, of which 6 months will be devoted to space segment commissioning, which is under the responsibility of ESA. So in the space segment commissioning, ESA and industry will assess the satellite instrument functionalities, operability, and performance against the space segment requirements, of course. I would like to stress that already in the planning activities, EUMETSAT is involved in the space segment commissioning, and we will be involved also during the space segment commissioning with our analysis to support ESA and industry. Then after the closure of the space segment commissioning, we move to the system commissioning, which is under the responsibility of EUMETSAT. So at this point, we will have to assess the system readiness to deliver validated level 1B data and level 2 products to the end users. Very important, of course, for all you people attending, and assess the functionality, operability, and performance of the entire system prior to commencing routine operations. So if we look at a timeline, this is, of course, let's say an ideal picture. We have the launch, LEOP, so launch and early operations phase that will be handled by not by EUMETSAT, but by an external entity. Then we have the beginning of the commissioning. As you can see, the space segment commissioning will start, and we will have actually an overlap at some point. We will not wait for the formal closure of the space segment commissioning to start system commissioning activities. What we need, of course, is only the stable production of level 0 data, because from this point on, we can test our system, which is of course the level 1B processing and the level 2 processing. And this is what we have described here. We will have a phase in which we will start testing, checking the content of the level 1 data. At the same time, we will be able to run also some of the CalVal activities. For example, if we think that in this phase already the background images and of course also DTs, these lightning events will be available, we will be able to do some analysis. Then we will reach a stable production of level 1 or level 1 data, level 1B data, formally speaking, and we will start also the level 2, let's say, product computation and analysis. So this is the way it's going to work. And as you can see here, in principle, we will have 6 months after at CRR, so the commissioning result review, and then 12 months at SCRR, which is the system commissioning results review. Now we are going to go into quite some details about what we are planning to do. Some of these may result trivial to you, but for completeness, I've decided to put it here anyway. In green, we are going to highlight the bullets on which we are either ready or we are currently working. The rest will be developed in the next years. So of course, there's going to be a very important tests related to the availability of the products as expected. So products must come with a certain repeat cycle, of course, with certain content. So we will do a check of what is called the level 1B data completeness, level 2 data completeness 2, of course, when we will have level 2 data. And at the very beginning, of course, sorry for putting them in a strange order, the very first test that we will do among these three is to check the DT data content at level 0 as this information comes from the spacecraft, because as we've mentioned yesterday, here is where we have the key information to do all the processing. So DT energy, position in the in the detector, timing information, availability of the background, all these thresholds and margins we talked about yesterday, and of course the availability of this information within the 3x3 window, which is very, very important for our processing. Then we can go, into something which is a little more, let's say, different from these, not focusing on the products, but on the coverage of the satellite that is, of course, evaluated from the background, from the background image at level 1B. So the idea is to do a check of how the LI is constantly covering the field of view that has to be covered above 84%. And also we will do a check on the coverage of the EUMETSAT member states that, of course, must be covered all the time, 100%. Then there will be quite some activity on the configuration of the detection and filtering parameters. This is a very important activity. And I would like to stress that on these, the LI instrument functional chain team is currently working. We still have to take a decision on how to approach this part of the activity that is crucial, because it will allow us to refine the performances of the instrument. And we will be working on this soon. So as you can see here, we have some tests that will be performed ad hoc during the beginning of the commissioning and will not constitute continuous monitoring. Myself, I will try to push for the continuous monitoring of the coverage, even though, I mean, this may not be necessary. Then we go into something which is much more important and interesting also for you. We have talked about lightning detection performances yesterday, how these are formally defined. But of course, yesterday we spoke about a theoretical evaluation of the detection efficiency of the false alarm rate and flash detection efficiency. Then there is the reality check. So when the instrument will be flying, we will have to assess these performances with a totally different approach, comparing the LI products against external sources, external references. So there will be many aspects related to the monitoring of the detection efficiency that you can see here. Of course, there will be the dependence on the radiance, on the background reflectance, analyzing the relation between lighting gradients and background reflectance, because as I've mentioned yesterday, due to the variability of the detection threshold, we will have a relation between these two quantities. Then we will have to try to assess the minimum detectable energy, the detection efficiency against external networks, as I've mentioned a few minutes ago. Also, the detection efficiency assessment using simultaneous detection in overlap regions. Yesterday, there was a question on this that I have answered. And as you can see, we have a method that is going to do this assessment. Then we will have a false alarm rate assessment, which can be a combination of simply monitoring the amount of information that is flowing through the system, knowing that up to level 2, the amount of information is strongly dominated by false events, as I've also explained. But also there will be an assessment of false alarm rate and flash false alarm rate using external data, for example, using this extended time window approach. Then there will be also the flash detection efficiency. As you can see, many of these bullets, I would say the ones that require much more time compared to the others in terms of implementation, we are already working on them, all the ones in green. Then there will be the assessment of the radiometric accuracy of the instrument. On this point, at this point, the responsibility will be shared between the LI scientific team, so our team, and other teams of experts that are doing this kind of assessment also for other instruments, for example, FCI, and they have also the tools, of course, to do this. So we will be employing the so-called G6 Deep Convective Cloud Calibration Method, where G6 stands for Global Space-Based Intercalibration System. We have a team working on this specific method that will be using it for LI. Then we will have the baseline for the monitoring of the radiometric performances of LI that will be based as it happens for almost all the visible imagers, will be based on desert targets. So this is also under the responsibility of the team of experts doing this in RSP, in EUMETSAT. And then we will have our intra-OC monitoring with statistical approach or pixel-based approach that we will present today in few slides. And also the direct comparison between LI and FCI. We know that FCI is going to be definitely characterized in a better way than LI, talking about radiometry. So, and the two, of course, they are on the same platform. They observe the Earth with different repeat cycles, but at the same time. And what we will do is we will be systematically comparing LI measurements versus FCI measurements. With an important caveat, we have to consider that FCI doesn't have on board, let's say, a 777.4 band, but we have a band which is close enough, which is the VIS 0.8 FCI band. So then we have some statistical methods for monitoring the DN histograms, meaning the histograms defined from the raw measurements were not even calibrated. So we will have different methods that will focus on the properties of the measurements, typically over 15 days of each single pixel of LI. So quite a lot of measurements. And as you can see here, these tests will be done during the commissioning, but they will run also for, let's say, the whole lifetime of the first LI and then the other instruments for long-term monitoring. Also, we have the assessment of the absolute sample position knowledge error, which, if we want to make it in very simple words, we're talking about geometric performances, baseline, not under responsibility of our team, again, under the responsibility of experts in EUMETSAT, landmark analysis on the level 1B background images. That's where I was mentioning, the difference between using a repeat cycle with 15 seconds or 60 seconds. So it can be different doing an assessment on different times. But we will also have under our responsibility some, I would say, simpler methods that will allow us anyway to do some monitoring against FCI. Also, these methods will run continuously. So more tests that we will be doing, lightning detection timing accuracy, against external data. Also, this is an interesting aspect because it's going to be tightly related to the navigation of the events. And we have already some results on this and derived with GLM versus GLD36 that are very interesting. Of course, we'll be monitoring the climatology of level 2 data against climatology that are already available. Of course, for this kind of analysis, we will have to wait longer periods. I would say at least of 1 month or half a year to do robust assessment over the climatology. We will be, of course, monitoring the number of DTs through the processing. This is an extremely important aspect, especially to understand how the ground segment is coping with such a big amount of information that will come through the system. Yeah, we will have, of course, specific tests on single filters. As I've stressed yesterday, we know that specific filters are meant to reduce the number of DTs that have specific properties. So we can check that, for example, the spatiotemporal coherency filter is indeed, as expected, acting on false events which are generated by random noise, radiometric noise, while, for example, the jitter we know is going to work on this chain of a jitter reconstruction filter is going to work on these chains of DTs along coastlines or cloud edges. A lot of monitoring aspects that are also related to lightning climatology, monitoring the group rate, flash rate, DT rate. This is very specific, but these two are, of course, actually one can also do this through the products. Each user can do this through the products. And then we will have the monitoring of the accumulated products against external data. On this, we will be working in collaboration with LIMAC members like Eric Bruning and Andrea Diamandi. And then, of course, there will be the monitoring of the instrument, I would say, key parameters, such as the dark current, readout noise, and offset. This will be done hopefully with a high frequency during the commissioning, and then, of course, during the routine operations, it will be done maybe twice, I think twice a year, if I'm not wrong. So conclusions, DLI commissioning preparation is ongoing. At the same time, in parallel, the implementation of the offline tools, OFTs, using the jerk of EUMETSAT for DLI commissioning is ongoing. As you will see from the presentation of Sven-Erik Enno, we are in a very good position, especially for assessing the LI detection, the lightning detection performances. And EUMETSAT, as I've stressed earlier, is not out of the game when talking about space segment commissioning, even though this is an activity under the responsibility of ESA. We are highly involved. For example, tomorrow we will have a workshop with ESA on this, ESA and industry on this. So at this point, I think we can either move on or have some questions. Thank you very much for your attention.
Thanks very much, Bart, for this introduction. I suggest we move straight to Sven-Erik's presentation and take questions after his presentation. I'd like to remind you all that you can ask questions on the Slido tool, event code #MTG-LI. So ask questions there anytime. We'll try to answer them either in this session or offline. Sven-Erik?
Yes, hello everyone. Can you see my presentation?
I can see your screen and the PowerPoint. Put it in presentation mode, please.
Is it better now?
No, it's not yet in full presentation mode.
Okay, should be better now.
Yes, now it's fine.
So hello everyone. I'm Sven-Erik Enno, and I'm going to talk about the LI Star tool, which is basically LI statistical and reporting tool. And yeah, I'm starting with very general introduction or overview or a block scheme of the tool, and yeah, just highlighting some important aspects. So starting from the input, so if we want to validate the LI against something, then we need external lightning data. So these are the names of the external networks that we are planning to use, or that we have already tested in some plots that I'm going to show. So basically, these are known to some of you for sure. So ATDNet, for example, is the UK Met Office lightning location system. Then Euclid covers most of Europe. GLD 360 is operated by Vaisala, and this is the only like truly global lightning location reference system that we can use to cover the whole field of view of the LI instrument. So this will be available, this reference data set, for at least 3.5 years after the launch. Then we have lightning mapping arrays, and then we have also some space-borne instruments, so ISS LIS, and of course GLM, which is the most similar instrument to the LI that is currently operational. And then for the LI itself, we will be using, of course, the lightning data groups and flashes, but also some background information for radiometric characteristics and performance, for example. And yeah, the important bit of LI star is so-called common data model. So the data comes in from different lightning location systems, and then it's processed to follow the common data model. And in this way, it can be used for all the LI star functionalities. So we have quite a few functionalities already in place, especially simple statistics and also detection efficiency, location accuracy. We already have lots of those. So I'm showing some examples in the following slides. And then, yeah, more specific to how we are handling the data and storing. So there will be a database, and it will be all integrated to chart the environment, which is something internal to EUMETSAT. But maybe it's also interesting to point out that actually the LI star can also run as a standalone Python application that you could basically run from the command line. So the output types that LI star can produce. So on the left, we have those output types or statistic types that use external lightning data. So we can do very simple statistics, such as time evolution of the number of flashes or groups, or for example, comparison of time evolution or spatiotemporal maps between different networks. That's going to be a few examples on the following slides. Then in the middle of the presentation, I'm talking about matching-based statistics. That's where you really compare DLI against other lightning location systems to answer questions like what it is relative detection efficiency or location offset, for example. And then at the end of the presentation, I have also some examples on the using the background data for radiometric performance, for example. So starting with very simple sanity checks that can be done using LI star functionalities. So here we have the same day and 4 different instruments, and just the spatial distribution of lightning colored by hour. So top left we have ATDNet, top right we have Euclid, and then bottom left we have GLD 360, and bottom right we have ISS LIS, which is quite different instrument with very short view times, so you can immediately see the difference. And yeah, it's a good initial sanity check as soon as we get the LI data to compare against ground-based systems and to check that it generally detects similar patterns in space and time. And if we have this, then we can move on and basically check also the accumulation of flashes or strokes during the same day, for example. That will show like where the highest accumulations are located and how these compare between different systems. And it will also highlight false alarms. As you can see top left, ATDNet has quite a few false alarms that show up as pink pixels, isolated pink pixels with very few, normally 1 or 2 observations. So this tells you again about the performance of your sensor, and it's very easy to do as soon as we get the data from the LI. And also to highlight that we can not only process small chunks of data, but also, for example, a month worth of data where we have tens of millions or even hundreds of millions observations. this is GLD 360 1 month flash accumulation on the left and GLM on the right. So it shows that we can keep up with the data rates, but also it teaches us, for example, that the GLM, which is very similar to the LI, detects monthly lightning patterns that are very similar to what GLD 360 sees. So we would expect the LI lightning patterns also match, especially at the flash level, the GLD 360 patterns. So a good sanity check again. And just to demonstrate that we can also create animations like that using more than 1 month worth of data, so hundreds of millions of GLD 360 observations in this animation. And then moving on into matching, where we can do detection efficiency and location accuracy. So the very basic principles. So first of all, we take one network or instrument and call it test network. So it's going to be LI, but right now we are using GLM in tests because it's the closest to the LI that exists. Then we take a reference network, for example, GLD 360, but we can choose any that is available. And then we set matching time window and matching radius. And all this is passed into the matching functionality, and it basically checks one by one each reference network observation and checks if there is at least one test network observation within the time and space windows from this particular observation of the reference system. If there is at least one, then the test system detected this reference observation, and we will save the data of the matching observations into a special file. If it didn't detect, then it was just this reference observation was missed, and there is nothing we can do. And then if we have done it for, let's say, a whole day, and we will have hundreds of thousands or millions of matches and observations, then we can compare, we can compute relative detection efficiency of the LI. We can compare the locations and compute its relative location offset. And these functions are already there. I'm showing some results, but we will be also developing false alarm rate functionality to assess the amount of LI false alarms against ground-based systems. So now some examples. So if we do just very simple exercise, ground-based network ATDNet against another more global ground-based network GLD 360, then we can get something like that. So the greener it is, the more of the GLD 360 strokes ATDNet detected, and in the red areas didn't detect much or it didn't detect anything. So it can be used in this case, for example, to nicely visualize the spatial range of ATDNet. Then moving on, we are also interested in diurnal changes in the detection efficiency. And here is a little demo how to detect or visualize those using LI star. So on the top row, we have hourly numbers of detections, top left Euclid and top right ATDNet, and it's the whole month, and each square is just 1 hour worth of data. So on the horizontal axis, we have days, and on the vertical axis, we have hours. And then on the bottom line or row, we have on the left Euclid relative detection efficiency to ATDNet, and bottom right, we have ATDNet relative to Euclid. And this is probably the most interesting one, because you can see that at night, ATDNet detection efficiency relative to Euclid is much lower than during the day. So you can clearly visualize the diurnal cycle. And in this case, it is known it's related to the ATDNet properties. But of course, for the LI, we want to also see if there is diurnal cycle in detection efficiency and how strong it is. So this functionality will help to visualize that particular issue. And then also some nice monthly plots. So here we are on the left doing GLM relative to GLD flash detection efficiency, and on the right GLD relative to GLM. So it's 1 month worth of data, tens of millions observations can be processed roughly in half an hour. And we can see some very interesting features. So for example, on the left, we can see this lower GLM relative detection efficiency in the northwest of the US, which is known and is related to the properties of GLM. Then another interesting feature is zero GLM detection efficiency on the Pacific to the west of South America. This is actually nothing to do with GLM, but we know that GLD 360 has some false alarms there. So it's not genuine lightning, and that's why GLM doesn't detect it. And of course, as a sanity check, you can see that outside this blue polygon, which is the GLM field of view, GLM, of course, sees nothing. So this is all red. And then on the right, if we do GLD against GLM, then actually all those red areas that are showing up are GLM artifacts. So GLM detects a lot of false events in these areas, and GLD doesn't see those events. So these faulty GLM areas show up in red. And this is basically, in this particular case, optical effects of GLM. And it has also some other problems, or at least it had in September 18 when this map was plotted. So it has some like horizontal bars that were related to how the data was read from the pixel array. So it's very important to demonstrate that we already have capability to detect all those GLM known issues, and it shows that we are ready as soon as we get the LI data to detect any issues in the LI data. And also location accuracy. So this is relative location offset between GLM and GLD observations in September 18. So on the left, there is north to south offset in kilometers, and on the right, west to east offset in kilometers. And the general observation is that the further you move from the sub-satellite point, the larger the relative offsets are. This is again in line with what the Americans have found out about GLM, and it shows that we will be capable of detecting all those offsets in the LI dataset. And now, in my last slides, a couple of examples of what else can be assessed and measured other than lightning data based validation. So this particular slide is about radiometric performance assessment. So we have the overlapping zones between the different cameras, and we can pixel by pixel and for each integration time just to do those comparisons to see how similar or different the background values of the different OCs are in the overlapping zones. And also very important, we have this geodisk requirement, or the coverage requirement, 84% of the visible geodisk, and also 100% for the European member states. So this is an example output of the functionality, LI star functionality, that is designed for monitoring this coverage. And this is the end of my presentation. So ready for your questions. Thank you for your attention.
Thanks very much, Sven-Erik. It's a great tool, and there's a lot of interest not only from inside EUMETSAT but also from others to potentially use this facility. I was very interested to hear that it's also available as a command line tool. We have a few minutes for questions. I'd like to remind you to ask your questions using the Slido tool. So these are questions to both of you, Bart and Sven-Erik. First one here, can users participate in the commissioning phase of LI?
Okay, so our main point of contact right now within the users community is the LI Mission Advisory Group. And we are already foreseeing activities that will support the EUMETSAT commissioning that will be under the responsibility of the LI MAG members. Okay. Apart from these, I don't know whether we are planning to distribute the data to a wider group of people. So at the moment, I think I cannot answer this question.
Let's go to the next one here. Will the L2 baseline and accumulated products already be available during the commissioning as test data sets?
Well, this is title. Okay, this is Andrei Diamandi asking, so a member of the LI MAG. So Andrei is in a very special position, so he may actually be able to access this data quite early compared to other users. But of course, for the rest of the user community, it may not be the same.
How is data dissemination tested during the commissioning phase?
Oh, this is a very nice question. Is not actually, I don't think it's for me to answer. Of course, the part of the dissemination setup and testing is not under my responsibility. So I guess this is under the responsibility of operations, actually. Yeah.
Okay, we'll answer all your questions offline if we can't answer them here. But please ask your questions using Slido and we'll get back to that. Let's take one more and then we'll do a short break. Will users be able to access data from LI Star?
Okay, when we say data, so as Sven-Erik presented, so we have data coming into LI Star, which are data that in principle are available, sometimes freely, sometimes, this data must be bought by a user. But I guess this question maybe is referring more to the results, maybe, or to the performance. So currently, LI Star is supposed to provide information about the LI performances only internally. But I have to say one thing, I mean, clearly in my mind and also in mind of our competence area manager, Sauli Ioro, there is the idea of publishing systematically on the web, especially during operations. Commissioning phase can be maybe a bit tricky moment, but during operations, we can do a selection of some of the results that, for example, were presented by Sven-Erik and publish them regularly online. This is something that can be done easily. Of course, I think USC also would be very interesting in supporting this activity because the results are available. It's just a matter of selecting them and publishing them on the web.
Yeah, we are in discussion on this in the user preparation project, and let's make sure it happens at a level that is useful to users. Okay, with that, I suggest we take a 3-minute break, and then we resume with the presentation by Jostelat. right, thank you, Regina. Hi, good afternoon, Jos. Thank you for contributing to this user preparation webinar on the LI and to report on some of your experiences and ideas around using this data from KNMI, the Netherlands. Floor is yours.
Thank you, Stefan. Okay, so first of all, I would like to thank EUMETSAT for giving me the opportunity to talk about our first explorations in the use of satellite data at KNMI. My name is Jos de Laat. I am a senior scientist at KNMI, and the work I'm going to present here is work that I've done together with Christian Wentig, who is one of our operational weather forecasters. KNMI is the National Weather Service of the Netherlands. It's the Royal Weather Service of the Netherlands. We have both operational tasks, but also do a lot of research and development. We have several research and development groups or labs, and we have actually a strong background in Earth observation. For example, KNMI is the principal investigator of successful satellite instruments like OMI and TROPOMI. The outline of this talk is that I will first start to talk about KNMI and why we actually are looking at GOES GLM data. I will spend quite some time on visualizations and first results, but also what came out of discussions we had with our weather forecasters. I will mention a few things about added value data products, and specifically short-term prediction and nowcasting, and then I will give a short overview of where we are currently at and what we have planned as our next steps. But first, why actually are we at KNMI looking at global lightning mapper data? Well, a couple of years ago, or actually last year, we started a KNMI project where we wanted to do more for developing or better use the available satellite data in operational weather forecasting. And the goal of that is that there is a rapidly growing amount of Earth observation data that can be used in operational weather forecasting, and we want to better translate data and information that is of use for our operational meteorologists, which means that we wanted to have a strong involvement of those meteorologists. And finally, we wanted also to start prepare for MTG, because MTG, as we have seen, will come and it will start to provide a lot of data. And we simply want to be ready for all that data. So we started a pilot project where we had 3 different sub-pilots. One was about spectrometer data, one was about numerical weather prediction data, and there was one project about lightning data. And why actually is KNMI looking at global lightning mapper data? Because the Netherlands is a small country and we definitely do not fall within the GOES discs. But a couple of years ago, KNMI was given the responsibility to do weather forecasting for a number of Dutch overseas territories in the Caribbean seas. And we do that now. So we do provide weather forecasts for a couple of islands. And as GOES already is operational, available, and we wanted to gain experience with new data and data products that will become available on MTG, we decided that it would be a good plan to look at actually GLM data and to see what we could learn from that and how we could incorporate that in our operational forecasting. Now, there were some sub-goals. One of them was that we also are developing a data portal for exploring all kinds of data. And I'll come back to that later. And we also have a large project that started last year, which is an early warning center where we want to start to provide all kinds of warnings for the Netherlands. And we need use cases to build that warning center. So that's sort of the background for why we are looking at lightning data. Now, within this project, we typically do things like start to explore literature and training material and manuals and look at applications that others have done with GLM data. What kind of data do they use? What kind of information do they extract from all that data? And what is most useful for operational weather monitoring and forecasting? And then the next steps are like, okay, where is the data? How can we obtain the data? How can we download the data? We have to start to make scripts for downloading and reading and processing the data, and then also make scripts for starting to explore visualizations and look at the data and information in all that data. And also, for example, compare with existing sources of lightning information that already is used by our weather forecasters. So first slide, first image that I made of the data. This is just one day of lightning data. You see part of South America here. It's a little bit difficult to see, and here are some of the Caribbean islands, and the colors here just indicate the time of when the lightning flash was detected. So, okay, we could read the data, we could plot them, and then we could start to further explore the data. And so one of the logical things to do was to start to combine it with other data. So logically, for example, infrared brightness temperature data. So that's the example shown here. And another logical step was to look at sort of level 3 data, sort of a heat map, or what is called flash extent density, where you simply divide the world up in small grids and then count over a certain period of time the number of flashes within that area. And that gives you an indication of where the flashes occur and where the most frequent flashing occurs, and how that relates to the satellite data or the cloud data that you get from other ghost channels. Now you can do that in different ways because there's a lot of information in the lightning data. So in this example, you compare actually 3 types of information. You again have the background, the cloud data from the ABI sensor. Then you have in color the detection of flashes, and the color goes from yellow to red, where yellow is the most recent one. And there are also some blue circles, and the blue circles are indicative for actually the area of the flash. And it gives you visually immediately an idea of when and where the lightning did occur, maybe a little bit of information of where the lightning is moving, but also how intense or how extensive the lightning is. So we started to explore that, and then the logical next step was also to look at the time development. And so what I will show in the next couple of slides are a number of animations that we've made of different visualizations. It will be the same scene in the same day for all 3 cases. But the first one that I show here is again the cloud data. On top of that, the flashes, which are now color-coded in the opposite direction. So red means the most recent, and yellow and white is further back in time. And also the circles indicating the magnitude of the area of the flashes. And if you then start to look at this particular scene, then there is a very active convective system here in the middle, which is slowly moving north. And if you look carefully, you will see that the number of flashes starts to decrease as this moves out of the scene. And then along a line here, at some point, a whole line of new active convective cells are starting to appear. Again, you see quite a lot of lightning in that area. And then it becomes early morning. There are a couple of small thunderstorms here over the ocean. And then as daytime progresses and the land warms, you will see daytime convection start to build up, which again starts to produce here some lightning, first on this peninsula, and then a couple of hours later also over the northern part of the Venezuela here. And you can see again, there are all kinds of cells that pop up and decay again as the convection continues to build and to develop. So that's one type of visualization that we looked at. Let me just pause for a minute, because one of the things that we see here is that we see that this is a very active convective system. Colors are very wide, but often forecasters would like to know more about exactly the cloud structures and how high the clouds are. So we looked at a different visualization. Again, same scene, same time period, but now what we've done here is we've color-coded the cloud tops that are colder than -50 degrees. And in this case, all you will see are just the lightning flashes over during the last 10 minutes with blue circles indicative of the area. And again, you see the same thing developing. You can see the dark reddish colors here, indicative of the coldest cloud tops, but you can already see that the colors here start to change from red to yellow. And then at some point, actually, the colors even disappear. And that's sort of indicative that the system is decaying. And then along this this line that we saw before, you see the new convection popping up, and it's quite active, and it must be some sort of a convergence zone. And lightning will continue, or the systems will continue to pop up here. And then as daytime progresses again over the continent, you will start to see the new convective cells starting to develop. First here over this area, again, you see the yellowish colors indicative of cold cloud tops. And then later over the continent again, like here, you see the convection again popping up. So that's another type of visualization that we looked at, and that gives you some different type of information that can be very useful. And then we did a third one, and the third one is the density map that I already discussed before, and that gives you an indication of where the real active cells are. In this case, the colors are indicative of the clouds with the most activity in the red. And what I've done here also is that if there has been no lightning over a certain time period, the transparency of the colors changes so that you sort of see the colors fade away over time. Now, again, the whole system is moving north, and now you can sort of detect where the real active areas were, but also how it is changing. You can see it start to decay, the colors turn yellow again, and the system, the active system moves out of the scene. And then along this line here again, convection starts to pop up again. It can be very active, very locally. So these are much more isolated cells here along this line. It's some pits, some active cores here. And you will see the same thing happening over the continents, over this peninsula area here, where lightning will start to occur here. Just about now, I think, exactly. And there are again some very dark red spots, some very active cores, but fairly small. The circles are fairly small in size. And then over daytime, over the other part of the continent, you can see the convection developing here as well. So these are sort of examples of the type of games you can play with that data. And like I said, one of the things that we are now looking into is actually to incorporate all this data into our GeoWeb portal. And the GeoWeb KNMI web portal actually is what we define as the next generation tooling for monitoring the atmosphere. And it's a web-based integrated system. It's built in Python code. It's going to be developed by by KNMI, but also at KNMI, and it's a tool that should serve the needs of both forecasters, scientists, and developers for visualizing and analyzing data. And if you look on Google and you look for KNMI GeoWeb, you get a nice overview of all kinds of pilots that we've done, tests that we've done with all kinds of visualizations that already have been developed. So that's the tool that we are looking into and focusing on. Now, that's one part of the story, but then I started talking to our forecasters, and they are already using data. So one of the tools they are familiar with is a tool on the site called Blitzortung. And I decided, well, let's present the data from GLM in that format so that immediately appeals to them and that they can relate to them. So this is an example here. You see South America here, Cuba is in here in the circle, and there's a part of Florida here. There's a lot of convective activity here over this region. There are some cells here over the ocean as well, and here at the border of Panama and Colombia, I think it is, there's also some lightning activity going on. This is 1 day of data, and the colors, I think there are 6 colors here, are indicative of lightning for a certain 4-hour time interval. And if I do the same thing with GLM, you get quite a similar image. It sort of detects the differences, but over Florida, Cuba, it looks very similar. You can also see, again, some areas over the oceans that look very similar. But what we also saw was that GLM said there was a lot of lightning over South America here, which did not show in the Blitzotton data. And those are sort of the things that you're interested in, like, okay, what's going on here? Is this something with GLM or is this something with Blitzotton? Are certain types of lightning not detected by one or the other? And so I did a little test, and this was just a test. So I removed all the low energy small flashes. And what then happens is that most of the lightning detections in GLM disappear. So this suggests that the lightning over this part for this particular day, South America, is relatively small in terms of energy and in terms of area. And maybe those are, for whatever reason, missed by Blitzotton. I don't know. It's still something I have to look into. But as a side effect, negative side effect, you can see that also a lot of lightning over Florida and over Cuba also has disappeared. So this is still ongoing. I have to check this. More research is needed, but this is sort of the type of thing that we looked into. So the status of our work at the moment is that okay, there is a lot of GLM data. It can be of immediate use for ourselves in our operational weather forecasting for the Caribbean islands. That's very good. The data will be very similar. As said, that will be provided by MTG Lightning Imager. It should be easy to set up a data stream, and it should be easy to make available for our forecasters in ways they are familiar with. We are currently looking at making this operational within this GeoWeb tool. And one of the things that I did not discuss, but which may make sense, is also to start looking at automated alerting. Now, one thing that in these discussions, what became very clear is that my colleagues, my operational weather forecasters, told me, like, often for users or for certain applications, the current information sources are sufficient, because often user needs differ from what a meteorologist is interested in, and that may differ from what scientists are interested in. That's especially the case for non-specialist users. But one of the things that then popped up is that they said, well, there's one thing that we find particularly interesting, and that is actually short-term predictability of lightning. And the reasoning here is a bit as follows. So the meteorologists tell me, like, okay, once there is lightning, we sort of expect that lightning will continue. Lightning is associated with cloud systems. And based on persistence, you would think, like, once a cloud system or a thunderstorm is starting to produce lightning, there is a fair chance that it will continue to produce lightning in the next 15, 20 minutes, half hour, or an hour. Also, with remark in relation to the moving of the system, lightning will be associated with clouds. And you sort of have an idea from all kinds of other data, satellite data, where clouds will be moving. So that's also less interesting to them. But knowing where lightning may occur, where it has not occurred before, is very important for them, because that's actionable information. For example, airports, if there's lightning, will have to start to apply certain rules and regulations in their operations. So for them, it's very important to know, even on a time ahead of 5, 10, or 15 minutes, if there's a chance that lightning will occur. So that is very important from them. And I started looking into that, and actually looking especially at what is being developed for GLM. Actually, such tools already exist. And I'm going to show one example of that. It's by NOAA and the Sims Institute, University of Wisconsin, and they actually already have a probabilistic lightning prediction tool for GOES GLM. And some details about it, if you want to know more, you can go to the website of Sims and look at their blog. But it's a deep learning model, artificial intelligence, and it predicts the probability of lightning in the short term, up to 60 minutes. And it's integrated in their PropSevere algorithm. And for the details, it's a convolutional neural network. It uses 4 AB channels. And it's very computationally efficient because you need to process a lot of data. But what it does is that it assigns the probability of lightning in the next 60 minutes to each pixel of the satellite image. And the way that looks like is an example shown here. So this is a particular image at a particular time. You can see some purple yellowish colors. That's where GLM has detected lightning in the past 5 minutes. And there are colored contours, and the colored contours are actually the confidence intervals of where their algorithm thinks that within the next 60 minutes, lightning may occur. So there's here at the border of Florida and I think it's Alabama or something, there's an area where this algorithm says there's lightning may occur East Florida, and also over the oceans, there are some areas where the algorithm says lightning may occur here. And if you then shift an hour later and you look at it again, then indeed you see that in these areas, lightning actually has started to appear. In Florida, also over the oceans, and also in this border region. So that's the type of tool that exists, and that's very interesting for our forecasters. And currently, we are now exploring the possibility to develop a similar algorithm at KNMI. And we're looking at how we can develop expertise and knowledge about this. We're also looking for some cooperation with some other people and looking for budget. Actually, we have the budget, but at the moment I made this presentation that was not completely clear yet. So we will look into this, but while preparing for this talk and also within the project we're doing, I also started to think about this within the European Union and EUMETSAT context. So one question I came up with me is, why should we actually do this? Should we do this? Maybe it's something that EUMETSAT would like to coordinate, because if it's interesting for us as a weather service or a weather institute, then it will be interesting for any European weather institute or African weather institute. Maybe it's something to develop then within the nowcasting stuff. I don't know, or maybe there are other weather services that have an interest in this. But these are things that are interesting, I think, to consider in preparation for the European and the MTG Lightning Imaging mission. Who will do what, and can we do it in such a way that it will benefit all of us? My last slide. So what we've done over the past year or so is we've developed expertise with working with GOES GLM data. We know where the data is. We have looked at visualizations, what we think is the most relevant data for us. We look at animations and how to combine different types of information for our weather forecasters, and we will start to implement this in our web portal, data portal, GeoWeb. From the users, we get back that especially new lighting is highly valuable for them because that's actionable information. And so we will start to look at develop a artificial intelligence type of algorithm for making short-term lightning predictions. Questions, as I said, maybe should we do this ourselves, or is there a role for EUMETSAT or the SOFs or other weather institutes? I don't know. And then finally, what we will do after that is that we will continue to explore the data in a more advanced way, because there may be certain applications or certain data or certain information in all the data that's available that could be used, but we'll have to talk to users and to our forecasters to find for those areas where there is clearly added value. And that's it. Thank you for your attention, and I'm happy to take questions.
Thank you very much, Jos. Great talk and lots of food for thought for people. I'm sure we cannot answer all the questions in this webinar. I think it's a good question to ask who in Europe can take this on, either individual services or in any coordinated way. Certainly the nowcasting staff is a place that is looking into some of these ideas. And but let's turn to some of the questions that we get from the audience. So the first one here is from Eric Bruning. Does the KNMI flash density product include information from the events to show the area covered by the flash, or is it only the density of the flash centers?
No. It actually uses the information included in the events about the area. That was the idea. So that's the way we used it, and it's indicative. I use the circle as a visually appealing shape to make it easily interpretable. So a small circle means low area coverage, and a large circle means a large coverage, basically.
Did you? So this is generated directly from the GLM products.
Yeah, it's already in the data product. So all you have to do is you have to read it, get it out of the data, and then combine it in the visualization you prefer, basically.
We get a comment here, next one from Pilar Ripodas from Spain, who's actually the Nowcasting SAF project manager. So she's commenting that the tool for lightning prediction within the Nowcasting SAF would be very interesting, could be connected to the Nowcasting SAF convection initiation product.
Yeah, so I definitely would like to, but I'll do that offline to get in touch with Pilar. It's actually on my to-do list because I think it would make sense in some point to think about whether or not that would be something to also do in the Nowcasting SAF. So thanks for that, and know that I will get back to you.
Yeah, and Jochen Ristius from DWD is also confirming this. There's a question here from Julien Zemmour. What are the modalities for accessing the Geo web portal of KNMI?
The problem is I don't know. That is my honest answer at the moment. But if you want to, or I will get back to that. I will try to figure out exactly how to answer that question because I think we're going to answer all the questions anyway.
Sure. Yeah.
So it may take a little bit of time because.
Question here: were you considering also calculating lightning jump?
I'm not completely sure what is meant here with lightning jump. Maybe
it's a rapid increase in the lightning rate.
Oh, yeah. Well, I had very briefly had a look at that, but it requires more research. But it definitely is something that is worth looking into because I think weather forecasters would be very interested in also identifying those areas where that happens, because those could be indicative of rapid intensification.
How would you correct parallax at KNMI, which is important for operational users, especially at airports?
I have a parallax correction, not yet at the moment implemented with the data, but I have an algorithm, or we have an algorithm for correcting for the parallax effect. But I will have to think about exactly how to do that. Because I think you can wonder if there is a real need for parallax correction for lightning, given that the area coverage often is much larger. Lightning can cover distances of tens to hundreds of kilometers. And I think, I wonder if there's added value in having a parallax correction for lightning. But again, good question, something to look into.
Let's take two more and then we'll take a break. We've had this one, we had this.
Yeah, so about Blitzautumn.
Do you expect advantage? Yes.
I don't know. I think it's something to look into. I think already we saw in previous talk that there definitely are biases in all instruments or all data sets available for monitoring lightning. And I think definitely that there's always, at least the added value would be to have different sources of information from completely different types of measurement techniques. But it will be interesting to see. I think one possibility could be, but it may be more of a research background, is that with the high frequency of observations from the lightning imager, you get a lot of time information that you may not get from other sources of data. I can imagine, but this is something that maybe people at EUMETSAT can confirm.
Yeah, and the extent of lightning flashes and also the duration of them, I think, is an added value.
Yeah.
From the space-based data. Let's take one more. I think we had an interesting one here from Bart. Actually, would you say that PropSevere with its prediction capability is more valuable than the GLM data alone for triggering action?
Well, the alone is not in the sentence. That's what you make of it, Stefan.
Sorry.
I think it depends on the users, on the type of user. So there will be examples. For example, the airports, for them, it's very relevant to know in advance where lightning will occur. But like I said, again, it very much depends on the user and the application actually of the data. It's sort of an added value data product, and you will have to see where it is useful.
Can I comment on this? Thank you,
Yes,
Jos, for the answer.
Bart?
Yeah, so this is a very important point because, yesterday we have talked about the LI timeliness defined as the time at which the lightning is detected and the time at which the data is available to the user.
Yeah.
So for GLM, if I'm not wrong, we are talking about very short time interval of about 20-25 seconds.
Yeah.
And for LI is going to be longer. And I know that internally, EUMETSAT, this has been, big topic of debate for a long time. But then you realize that, then there is a tool like PropSevere that, of course, is going to look into the future. So there's no way you're going to beat that timeliness. So you wonder, shall we really get stressed to reduce the timeliness down to 20 seconds? Especially when we know that we're going to use accumulated products refreshed every 1 minute. I think this is something we will have to understand.
Yeah. No. So if I look at PropSevere, what they provide is a prediction of the chance of lightning within the next 60 minutes. So I think that already indicates that there's a limitation on the predictability that you have. And I think for timeliness, whether or not your data is 20 seconds old or 5 minutes old, if your prediction window is a integration over 1 hour, I would not expect that to be too relevant there. But it's something you could test actually with GLM. You could simply put in a delay when you start to look at GLM data and see if that matters a lot.
Yes, right.
But I think my guess would be that the refresh rates and the fact that you will have so much information every 20 or 30 seconds may be more important than the timeliness actually. But it's something to look into, to keep in mind when further looking into the possibilities of prediction.
It's very important for us to know these trade-offs. Yeah, thanks very much, Jos. This was very, very good, triggering lots of good questions, and we have more. We'll answer them offline. I'll take a 3-minute break, and then we resume with the Meteo France presentation.
Thank you.
And please respond to our survey, the poll on Slido. We'd like to make this experience useful to you. We're always open for suggestions and improvements, so please respond to our 5-question poll on Slido. Thank you. Hello, welcome back, and we'll come to the last talk of this user preparation webinar on the MTG Lightning imaging mission. We have 2 colleagues from Meteo France with us, Sylvain Lemoyle and Jean-Marc Moisselin, and I'm looking forward to your presentation now. The floor is yours.
Okay, thank you, Stefan. Yes, thank you, Jean-Marc. Thank you, Stefan, and thank you all for coming today. I am Sylvain Lemoyle from Meteo France, Satellite Center for Meteorology, with my colleague Jean-Marc Moisselin from Meteo France Toulouse. We will present to you in the next slides a wide use of lightning data in Meteo France. I would like to thank the various contributors who help us to make this presentation. A wide use of lightning data. It's a wide variety of networks, ground or satellite networks. The satellite data from the GLM sensor on board GOES 16 and 17 for now several years. And of course, MTG LI expected in the upcoming years. For the satellite lightning data, we are interested in standalone mode, in data fusion approach, and for NWP. The presentation are the 3 parts: the use of the raw products, the data fusion approach, and the lightning data for NWP. Let's begin the part 1, the lightning data for the forecasters and the media. In a few slides, I will present to you 2 different ways we use at Meteo France to display the lightning imager products from GLM, the global lightning mapper from GOES satellites. The goal is to adapt the data to the public. First, to the forecasters on their Synopsys workstation they used to work every day. And the second way to the media and for general public information. For all of them, we've chosen to display only the information from flashes. We collect from our EUMETSAT receiving station the GLM L2 products from Go 16 and 17 with a 20-second refresh rate in NetCDF format, collected in compressed files of 5 minutes. From these input files, we extract the flash information and create a GeoJSON file every 5 minutes to display an image of accumulated flashes on Meteor France workstations. So for one flash in the GeoJSON files, we have mainly the coordinates, the area, the energy, the duration, and the exact strike date. So we can display this kind of image of our forecaster workstation. You have an example on the right part of the slide. Each dot is corresponds to a flash within a 5-minute period. And as you can see, we use 6 colors. It depends on the timing of the flash within this 5-minute period. And for each flash, it's possible with a right click to access information contained in the GeoJSON file. So you have, for example, the image date, the flash duration in millisecond, the flash energy in joule, the flash area in square kilometer, and the exact flash date. An example of 30-minute animation. Of course, in the next slide, the forecaster is able to superimpose the lightning data to satellite images and make animation, whatever he wants to display, visible or infrared, color composite, or geocolor images. For the media, we've chosen to display the flashes in a more realistic way, as close as possible to lightning flashes seen from space. As for the forecasters, we process only the flash information from the GLM L2 products because the process would take too much time if the lightning flashes were created one by one from the events or groups. So we use a single pattern, as you can see on the slide, with the possibility to choose the color, where the size and opacity depend respectively on flash area and flash energy. The size of the pattern is adapted to the flash area and to the scale of the image. And for the opacity, we use 50% opacity for the weak energy to 100% for the strongest energy values. And this is an animation of on my last slide. This is an example of an animation over the South America. This is a visible image with lightning data patterns, but we can choose to superimpose this kind of lightning data over geocolor images, for example. So thank you, and I give the floor to Jean-Marc for the next parts.
Jean-Marc, we cannot hear you. Jean-Marc, we cannot hear you. Okay.
And now?
Yes, now it's good.
Perfect. Okay, so I have some difficulties. I will switch off the camera, the video. Okay. And
no problem.
Okay. And I think I have to restart the lecture. So sorry for that. So is it okay now?
Yes, very good.
Okay, thank you, and sorry for the problem. So I will now talk about the data fusion product, and it will be illustrated by RDT product. RDT is a rapidly developing thunderstorm. It's an object-oriented approach, adding value to satellite image. It is a product of the operational software maintained by EUMETSAT Satellite Application Facility for nowcasting. And here you have several versions. The last version is version 18.1. It is compliant with GUS 16. And RDT will be used to illustrate a data fusion product for the webinar. So there is a 4-step algorithm inside RDT for the detection of cloud system, second part, the tracking of cloud system, and then the discrimination. The goal of discrimination is to answer to the question, which clouds are convective or not. And then there is a forecast up to 1 hour. And there is an attribute calculation for each RDT cell. Lightning jump is calculated inside each RDT. IWC hazard, it is from KNME algorithm, overshooting top calculation, etc., etc. So we want to move toward a 3D description of convection. So RDT is a question of software inside NWCSAT, but it is also a question of production by each user of RDT. And among these users, there is Météo France, and there is a RDT production for several satellites. We have a production with GUS 17, with GUS 16, with MTG 0, with MTG IODC, and with Himawari 8. And mixing these several production, taking into account the shift between the satellite and the differences in cadency, frequency, we have the possibility to provide convection global map thanks to several satellites and this RDT production. And in RDT, with RDT, we are able to detect convection without lightning data, but if we have some lightning data, we use it in RDT. And we use several network, ground-based network, like WWLLN from University of Washington, the Vaisala GLD 360 that has been quoted several times in this webinar. We use Meteorage over Europe, and we use sometimes some local network. For example, here on the east part of the slide in Nouvelle-Calédonie. And we mix we use this several network, and we integrate them in RDT to describe the convection or to calculate the lightning jump, for example. And you can note that we use also space-based lightning information from GUS 16 and from GUS 17. And we make up this kind of data as if they were ground-based lightning network to ingest them inside the nowcasting SAF software. So there is a lightning jump algorithm in RDT. So as Stefan said previously, lightning jump is based on lightning rate analysis at a fine time scale. Second, the first step is pairing lightning data with the RDT cell, and the jump is realized if two conditions are realized: a lightning rate above a threshold and an acceleration of the lightning rate during 12 minutes. And it has been implemented in RDT version 2018. And here you have a series of lightning data inside a RDT cell, and jumps are calculated with the rule here and are associated to the cell for each radiometer time slot. And this cell, this long life cells, more than 7 hours, has several jumps, and it has been associated to a Hell event. And indeed, the lightning jump is proven by literature to be a proxy to severe weather hazards like hail, gust, etc. So it proves that it is interesting to have a lightning jump in calculation inside RDT. Validation of the lightning jump is not very easy because, for example, we need some hail events, and to validate our lightning jump process, we use USSL database or HYDRE project, HYDRE data, a Météo France data fusion product based upon radar, polarimetry, several sites, use of temperature profile, and so on to estimate the L hazard. And for example, here we have all the convective cell for 1 day, and here the cell only associated with lightning jump. So they are not lightning jump for all the cells. And you can see that we have some heat here because pixel with detection of L by radar-based product are close to the lightning jump RDT cell, but of course some myths and some false alarm. But the question of the quality of reference in such studies is open. So RDT in itself as a detection of convection tool is compared to lightning data, and the identification of convective phenomena as a POD of above 70% during spring and summer. And there is also an early diagnosis. It means that 25% of RDT convection diagnosis is provided 15 minutes before the first stroke. So, in this context, what LE will bring? What is done with GLM or ground-based network will also be possible with LE. So, it means that we'll go toward a better description of convection in addition to ground-based lightning network, a better tuning, a better real-time mode, and a better validation. And a crucial issue could be solved: the validation and tuning of RDT over Africa, where we are almost blind concerning the validation. Lightning data can be used also in NWC-SAF product. Lightning data are already used by convective rain wave and RDT. It is used by CI, convection initiation, for validation purpose. The next delivery of NWC-SAF software will include a GLM reader. It will be this year. And NWC-SAF reader will read both GLM and ground-based lightning data. It will allow comparison, and it will enrich the description of convection, not to substitute. Lightning imager product development is planned by NMA of Romania in CDOC 4, still in the evaluation phases. So let's talk now about NWP product. What can Lightning data bring to NWP? So thanks to Météo France contributors for this part. So we first start with Lightning data assimilation, and the objective is the preparation of the assimilation of MTG Lightning imager data in AROM France. AROM France is Météo France limited area model. So here you have several references in terms of project, exerb or solid, and PhD TDs, and at the Research Center of Météo France and Laboratoire d'Aérologie, and mainly Frédéric Hermann and P. Combanus recently. So data are lightning imager pseudo observation created from meteorage data using machine learning algorithm. So we simulate real lightning imager data with the scientific value, of course. And the data assimilation system is built like this. There is an observation operator for flash extent density, and it is based on vertically integrated global maps accordingly to literature. And then in AROM France, the flash extent density is converted into relative humidity before assimilation in 3D VAR, following the works from Comment et al. And it is a technique, it is a method very similar to assimilation of reflectivity in Météo France. So let's move to an example. Here we have simulated flash extent density, and here we don't have simulated flash extent density in the background, but in the observation we have no flash extent density, and here we have. So if we see the result inside the integrated water vapor image changed by lightning data assimilation, we can see that here we can add humidity where lightning were observed and non-simulated, correspond to here. And here we have a decrease of humidity where lightning data were not observed but simulated. So it proves in these cases from the thesis of Erdmann that the goal is reached. Indeed, the assimilation of lightning data improves the analysis. Let's see now what we have in terms of scores. The fractional skill scores is used for these topics. So for two parameters, rainfall and flash extent density. If we focus on rainfall, we have a blue line. It's for radar data assimilation, still operational only. Lightning data assimilation is in orange, and radar plus lightning data assimilation is in green. Of course, there is not so much difference between the curves for low level of precipitation, but if we focus on a threshold of 10 millimeters in 6 hours, we can see that here the green curve, that means when we assimilate both radar data and lightning data, is above both curves, only radar data or only lightning data assimilation. And sometimes Lightning data assimilation only is better than radar data assimilation only for the highest precipitation. So it is very interesting to have this assimilation in future, and it will improve the AROM limited area model. So we talked about assimilation. Let's now move on to lightning diagnosis. So the idea is to have a lightning diagnosis as an output of the numerical model. So it is done both in AROM model and in ARPEGE model. So in AROM, the limited area model, non-isostatic, it comes from several works, and the variable is total lightning. It's called F1. It is coded since September 2019, and now it is in test by forecasters for finest tuning. And it is in parallel, it will be in parallel production for the final evaluation study during spring 2021. So the total lightning variable, F1, is based upon global flux at -15 degrees Celsius in coherency with the electrification processes inside clouds. So here it is a flux, and here it is a constant. This is called K1, and it is the value of the constant. And this is the post-processing we will use to have a total lightning F1 for forecasters inside limited area model AROM. And in ARPEGE, it is a global model with lower resolution. We will use a set of parameterization, a series of parameterization of proxy, and we use parameterization of Lopez and using CAP, vertical extension of clouds, and a proxy for electrical charge. At the end, if we consider 24-hour flash, oui?
Yeah.
I'm almost at the end. Is there a problem? May I continue? Okay, I continue. I hope you can hear me. Stefan,
I can hear you. I didn't hear you for about 10 seconds. Just keep going.
Okay. I would say that there is an output of lightning for ARPEGE and AROM model, okay, to help forecasters to have a forecast of lightning activity. And here it is 24-hour accumulation for ARPEGE on the left part and 24-hour accumulation for AROM on the right part. And the verification is provided by Meteorage. And you can see that lightning forecast by AROM has a better resolution than ARPEGE. Of course, it is normal because AROM is limited area model and ARPEGE is global. And you can see that fine structure that you can see here in Meteorage, for example, here in Spain, can be seen by AROM model. So it's very interesting for forecasters to have in future this diagnosis coming from model output. And of course, lightning imager will help to tune or to validate this lightning diagnosis when it will be available. So let's now move on to the conclusion. So there is already a wide use of lightning data in various domains, diagnosis, nowcasting products like RDT and NWP. So NWP, there is assimilation and diagnosis. Assimilation, well, it's more for future, and diagnosis is for this year. and work based upon ground-based lightning network, or GLM, will be adapted to LI in future. So thank you for your attention.
Thank you very much, Sylvain and Jean-Marc, for this presentation. It's a very wide use of lightning data in Meteo France, and some great projects ongoing, also in the area of simulating data. So let's look at the questions we are getting. Yeah, let's look at this first one here. I'll just make it larger. What has been the feedback from Meteo France forecasters when using the GLM products over the Caribbean?
Oh, the feedback is pretty good. We have French territories in French Guiana, in Martinique, Guadeloupe, on Saint-Pierre-et-Miquelon, on the French Polynesia, in the GOES 17 area. Yeah, the feedback is good. There are known problems in some areas, and we don't know why, but it seems even better than some ground networks sometimes. So yes, we expect the same or better with MTG LI for France.
Very good. I like the word that Jean-Marc used, to enrich information for forecasting. I've heard this also in testimonials from forecasters in the US National Weather Service, that they saw the value of GLM gridded products in adding situational awareness and in aiding in decision making, adding a bit of lead time based on sources of information such as brightness, temperatures, radar echoes, and others, as if they compared to if they didn't have this information. So it's enriching existing information. There's another question here. The RDT data, Jean-Marc, you presented the rapidly developing thunderstorms product as part of the nowcasting SAF software. In which format are these available?
The official format is NetCDF. Can you hear me? I think everything is frozen.
I hear you, Jean-Marc.
Okay, so the official format of most of NWC SAF product, including RDT, is NetCDF.
Thank you. Question here between hailstorms and lightning. It's on lightning activity.
Yes. As I said, there is two ways to validate lightning jump. To use a French product called EID, and another one to use USSL database. And we plan to have complete studies and a scientific report that will be written inside the NWC SAF context, and will be available for everybody. Yes, we plan to do it by the end of this year to have a complete report of validation of lightning jump.
You showed the work on data assimilation, and I was interested the total ice water path to Graupel was used to later use LI data with that. Is that observation?
Sorry, Stefan, but I only catch 10% of the question due to connection issues.
You mentioned can you hear me now?
Yes, better.
You mentioned the development of an observation operator.
Yes.
For the AROM model.
Yes.
Can you comment on this development? Is it done in only Météo France or within the Aladdin consortium?
I don't know if it is spread by inside the Aladdin consortium. I suppose there is no obstacle for that, no problem for that, because this is part of the development are shared, and well, I can put a reference on Slido for that. It's a reference for reflectivity, but it's almost the same from flash extent density. And as I said, it is development for the moment in research. It is not implemented, and it will be available for future. Still in research and development phases, because the thesis has just ended 2 months ago.
It is a very interesting development. So far, we have mostly associated FCI radiances and wind products with NWP and not so much LI. So I'm very interested in this development from the MTG imager. Okay. We have another question here. How do you test your RDT algorithm in winter conditions?
Again, with lightning data when they are, and so it's very difficult to test it in winter conditions. But that's the reason why the scores, the POD, are less relevant in winter conditions, but still with lightning data. And of course with expert studies, case studies, and so on. There is a complete report on RDT validation and the full scores value for all the season inside the NWCSAF website. But as I said, the verification of RDT is challenging when we don't have some lightning network. So problem is not a question of season, it's a question of lightning network, especially for sparse covered regions like Africa, as I said.
And Sylvain, today in this second day of the user preparation webinar on LI, I hope you could hear me throughout. I heard there were some bandwidth problems. I hope it's been okay for you. It's been a great session today. Please don't forget to respond to our session poll in Slido #MTG-LI. I'm drawing a close on this second day. Thank you for attending. And we are planning further user preparation webinars on FCI and the other observation mission on MTG and also EPSSG. So with that, I'd like to close the webinar and wish you a good rest of the day.